Hello, and welcome to Aggressive Physics. Today is day 59. What I'd like to discuss today is figuring out the relationship between variables in an equation. One of the things that physicists often have to do is see how different variables will affect the outcome of another variable. For example, if we're trying to determine whether or not to change a speed limit, we're going to want to know how much more energy is involved with cars traveling an extra 10, 20, or 30 miles per hour. We're going to want to be able to determine how fast cars can travel around exit ramps. So we want to be able to build them to the proper specifications. Now, that means if someone's speeding instead of going 30 miles an hour on an exit ramp and they go 40, will that cause them to fly off the road? So not knowing certain variables and determining how much it's going to change is something that we still do and find useful. Now, Newton had to do this because G wasn't discovered until well after his death. So he was able to figure out the force of gravity, the gravitational attraction between objects, to a degree, but not to an actual value. Now, we can do the same thing now. What we can do is use his equation and change the variables that we're going to change and see how that affects the final force. Now, there's a process by which we typically do this. And what I like to do is I put in ones for everything that stays the same, and I'll put in the variable that changes in for the numbers that are going to change. For example, if I double a number, I'm going to put the number 2. If I half the number, I'm going to put a half. If I triple the number, I'm going to put a 3. And if I quadruple a number, I'm going to put 4. Every other variable that stays the same stays as a 1. And physics assessments love to ask questions about relationships between variables. In fact, for some tests, that could be 5 to 10% of the entire test. You don't even really need to know how to use the equations or what numbers to plug in where. All you need to know is if I put a 2 in here and a 1 everywhere else, how is that going to affect the number that I am looking for? Now, Newton's law of universal gravitation is a classic one that will be asked on assessments because there's so many variables involved. Now, what you'll do is you'll put a 1 for the big G because that never changes. It's a universal constant, so it stays the same forever. The masses can change. If they don't, you put a 1. So you put 1 times 1, or 1 times 2, or 2 times 1, or whatever the combination is. And then the distance between them may stay the same. If it does, it's a 1. It may double, it may triple, it may halve, it may quadruple. It may be 1/16. And what you'll do is you'll put that number in place of the D or the R, depending upon the equation you're using. Now, what I have are a couple of example problems that I'd like to look at. And for the first one, if we double the mass of a single object, what's going to happen to the final force? Well, big G stays the same. That's a 1. We'll double the mass of object 1, so it's 1 times 2 times 1, which is going to be mass 2 stays the same. And the distances stay the same, all divided by 1 squared. So if I do 1 times 2 times 1 over 1 squared, I end up getting 2. So my answer will be doubled. So if I double the mass of a single object, I'll double my final answer. On the other hand, if I double the distance between the objects, the big G is a 1, the mass is a 1, the other mass is a 1, so it's 1 on the top. I'm going to double the bottom number, so 2 in for D or R. But remember, it's squared. So it's going to be 2 squared or 4. So the answer would actually be 1/4 or quartered. Now, there are a couple of more sample problems I'd like to look at. If we triple the distance between the objects, G is 1, mass is 1, the other mass is 1, and I put 3 squared, which is 9. So that'll be 1 on the top, a 9 on the bottom. So 1 over 9 is a 1/9. Now, you can change more than one variable at a time. Of course, in a scientific experiment, we typically want to keep everything else controlled and only change one thing at a time. But on assessments, you're not doing laboratory work, so a lot of times they'll change more than one variable to see if they can trick you. Now, in this case, let's double the mass of object 1, triple the mass of object 2, and then triple the distance between them. G is 1, mass 1 is 2, mass 2 is 3, so that's going to be a 6 on the top. 1 times 2 times 3 is 6. And then divide that by 3 squared, or 9. So you end up with 6/9. Now, typically what you'd have to do then is simplify it to 2/3. So finding relationships between variables is an important skill to have. All you have to do is put ones in for the variables that stay the same and the number of how much you change the other variables in for those variables. Double, you put a 2, triple, you put a 3, quadruple, you put a 4. If you half, you put a 1/2. If you make it a third, 1/3, and maybe a fourth, 1/4. And any combination thereof. Don't forget to square the bottom r, because there's two r's that you're actually changing. You're changing the r squared. Being able to do this will allow you to see quickly how different variables will affect the final answer, and it will get you a number of points on any physics assessment that you're asked to solve. Thank you. Let's calculate the force of attraction between the Sun and the Earth. Why does the Earth stay in orbit in the first place? Well, the Sun has a large mass, and it's 2 × 10⁻30 kilograms. That's the mass of the Sun. Mass of the Earth we've already talked about, and we're going to use 5.98 × 10⁻24 kilograms. And the Earth is quite a ways from the Sun. The radius of its orbit is approximately 1.5 × 10⁻11 meters. Now, if we know the mass and the radius, we can just calculate the force of gravity, which is big G m over r squared. 6.67 to the -11 Newton meter squared over kilogram squared times 2 × 10⁻30 times 5.98 × 10⁻24 all over 1.5 × 10⁻11 meters quantity squared. Now, as you can see, the scariest part of using this equation is the fact that we often use objects that are really big, so the numbers just become unmanageable. 6.67 e -11 times 2e30 times 5.98 e24, and we get a number 7.98 to the 44 before we divide by 1.5 e11 squared. And when we do that, we end up with the force of gravity between the two to be 3.54 times 10⁻22 newtons. So the Earth stays in orbit around the Sun because the force of attraction between it and the Sun is so large. 3.54 times 10⁻22 newtons.